Good day to you. In other modules, we've been speaking about the Young's modulus of elasticity and how it governs the relationship between stress and strain. And we emphasized in those modules that the Young's modulus is an object or is a property of materials rather than objects. Objects have shapes, they have dimensions, and all those are very important, but Young's modulus is a measure of a material property. And so irrespective of how big, say, a bone is or what shape it is, all of those bones will have the same Young's modulus. However, you cannot say that shape and size don't matter to the mechanical properties of bones. They very clearly do. And what we're going to do in this module is discuss how shape and size of an object actually can influence the mechanical properties of an object under a reasonable kind of biological regime. The first thing we want to do is we want to demonstrate on our friend Twiggy over here how is it that the kinds of mechanical objects, in this case bones, how they actually experience stresses and strains under a reasonable biological condition. And so what we're going to do is we're going to look at the strains on this bone right here. This is the femur, obviously, and it's attached to the pelvis over here. And you can see that the pelvis is quite a large flange-shaped organism, or flange-shaped object. And what I'd like to do is to illustrate for you how it is that, this bone is deformed under the typical kinds of forces it will experience. The first thing we're going to look at is muscle, where muscle comes from, where it goes. And in the case of the muscles that move the bone, the femur, this way, that is, flexes it up towards the body, there's a large muscle that attaches to this flange of the pelvis up here, and it comes down and attaches on this surface of the femur right over here. Now, if we want to look at this analytically, then we can say that there are basically three forces that are operating on this bone. We have a pulling force that's operating in the mid-shaft of the bone, and then we have 2 points, one at the attachment to the pelvis and the other at the attachment to the lower leg that are acting in the opposite direction. And so if a muscle here pulls on the bone this way, that's going to be opposed by forces acting at the pelvis in this direction and at the knee in this direction. Now, this is known in engineering as a so-called three-point test. And if we come along here and we look at the ideal three-point test, the machine takes something like a rod and it suspends it between 2 points. And then it applies a force at a third point. That's why it's called a three-point test. So a force is applied from here. And when that happens, the bone will deform, or sorry, the rod will deform. And this is going to be exaggerated quite a bit. The deformation will operate this way. That is, you'll be pushing down on the bone like this, and the bone will bend between those 3 points. 2 points of resistance and 1 point where you're applying a force. And the kind of deformation that you get in that kind of a three-point test is called flexion. And one of the important properties we need to know is something called flexural stiffness. And if we come back here to Twiggy, we see that the bone here is going to be experiencing a kind of flexion when it's flexed between these 3 points, the point here of attachment at the knee, the point of attachment at the pelvis, and the point of attachment and force application at the middle of the bone. Okay, now the flexural stiffness of an object, this is where properties like the length and the size of the bone or the rod come into play. And so, for example, if you look at the kinds of dimensions that affect the stiffness of an object, one important one is the length of the object. And in the three-point test, it's between the 2 pivot points on either side. But in the case of Twiggy over here, in the case of Twiggy, the length is going to be basically the length of the shaft of the bone. Now, if you look at the flexural stiffness, and let's make up a number for, or a symbol for this. Let's call the flexural stiffness phi for the Greek equivalent of the word F. And one of the interesting things that you find is that the flexural stiffness of an object is proportional to its length. This is an intuitive kind of idea. The longer something is, the floppier it's going to be. And the interesting thing about it is that the flexural stiffness is inversely proportional to the length. And what's remarkable is that the flexural stiffness is proportional to the length cubed. This is a very important feature in understanding how bone size scales with body size, for example. And so the longer you make something, the more floppy it is, the less flexural stiffness it has, and it is proportional to the cube of the length, so that if you double the length of an object, you're making it 2 cubed or 8 times more flexible, or 1 over 8 times stiffer. Okay. Now, clearly the Young's modulus of elasticity is going to have a role here as well. It seems quite also intuitively obvious that the more compliant a material, the less stiff it's going to be, and the greater the Young's modulus, the stiffer it's going to be. So if we want to calculate a proportionality between the flexural stiffness of an object and the Young's modulus, then this is again going to be proportional to the Young's modulus. The stiffer the material, the stiffer the material, then the stiffer the object will be. That is, the less flexible it will be. All right, and so that's another property. And so there is an object property, namely the length, and a material property, the Young's modulus, and those two things interact in such a way that the flexural stiffness is going to be determined in part by the ratio of the Young's modulus and the flexural cube of the length of the object. Okay? All right, now there are some other things involved as well, and these have to do with the distribution of material within the object. And here our discussions in another module on cantilevers comes into play, because as we've seen, when you have an object that is bending under a strain, that is undergoing flexion, that most of the material on the inside is actually so-called parasite material. It's not bearing any strain, but rather it's just adding weight to the object. And most of the strain is being borne by material peripheral to the object. Now, we've encountered this already in the concept of the second moment of area, and let's just briefly review that. The second moment of area is a measure of the distribution of strain-bearing material in an object, and let's compare 3 objects. Let's compare a disc, for example. Let's compare a flywheel that has most of its material distributed around to the outside. And let's compare a flying saucer with most of its mass distributed to the inside. Now, each of these is going to have a center of mass. In each of them, it's going to be the geometric center of the object. If you look at the cross-section of these things, they're going to look something like this. In our flywheel, most of the mass is going to be distributed out here. And in the case of our flying saucer, most of the mass is going to be distributed in the center. It's pretty asymmetrical, but nevertheless you get the idea. Now, the second moment of area is basically a measure of where the average center of mass away from the center of mass of the object is. So if we draw a dotted line indicating where the center of mass of the object is, the second moment of area tells us on average how far away from the center of mass that material is. So in this instance, in the case of a disk, our second moment of area is going to be about midway from the center to the edge of the object. In the case of our flywheel here, the center of mass is going to be located out towards the edge. And in the case of our flying saucer object, the second moment of area is going to be located quite close to the center of mass. So second moment of area depends upon the distribution of of mass within an object. And when you're talking about the quantity here, this will have the largest second moment of area. Our flywheel, our flying saucer shape, will have the smallest second moment of area, and our disk will be somewhere in between. Now, when we spoke about the second moment of area before, we were talking about its relationship to angular momentum, that is, rotational speed. But it also has an important influence on understanding flexural stiffness as well. And here's the relationship right here. If you look at the distribution of mass in a typical bone, you're going to see that if you cut a bone in cross-section, you'll see that there's going to be material, and there'll be boundary here between the bony material, indicated with our cross-hatching here, and then a center material which in most bones contains bone marrow and those sorts of things. And when this kind of an object, and just keep in mind we're talking about cylinders here, when this kind of an object undergoes flexion deformation, most of the load is going to be borne in the material at the periphery. Now, where this comes into flexural stiffness is that the flexural stiffness of an object is also directly proportional to the second moment of area, in which case we symbolize it as an I. So now we have three things that feed into the into the flexural stiffness of an object. We have the length of the material, we have the Young's modulus of elasticity, and we have the second moment of area. And what we can do is we can calculate a formula. Again, there's nothing complicated about this. We can look at our flexural stiffness, look at all the things that feed into it. And in the case of our flexural stiffness, we are looking at a proportionality that considers the Young's modulus of elasticity, the second moment of area, over the cube of the length. And so what really determines the stiffness of an object is this product of the Young's modulus, the material property, and the second moment of area, which determines its distribution. Things that have a large second moment of area and a stiff Young's modulus will resist flexural stiffness much more than those that have this smaller product of those two quantities. And of course, the longer it is, then the more flexible it's going to be. Okay, now let's have a look at some real bones here and illustrate this principle in action. I have three bones here. We have a human radius here, and we have a human femur here. And the lengths are a little bit different, but what is really striking about these two bones is that the diameters of those two bones are really quite a bit different. This is a more gracile bone, if you will. It's more slender, it looks more graceful, and this one is thicker over here. Now, in part, this reflects the fact that the femur has to experience much larger strains, much larger flexural strains as part of what it does than does the radius. The radius picks up loads that we can pick up and carry in our hands. At best, we're looking at things that can be flung about like missiles or projectiles or baskets of food or those kinds of things. But this bone here doesn't have to experience the same kinds of loads that this bone does right here. And the product of the Young's modulus and the second moment of area in both of these can be calculated, and the product is going to be greater in the femur than it will be in the radius. Despite the fact that they have the same material, it's all bone, it all has the same modulus of elasticity, the flexural stiffness is going to be greater in the femur than it will be in the radius, primarily because this is wider. The second moment of area is larger in this bone than it is in this bone. And of course, we can come along and we can compare these two bones here. This is a femur of a cow, and again, this is the femur of a human. And obviously, cows have to sustain much larger loads, and the lengths of these are, this one is shorter, but it's not that much shorter, but the diameter of this is quite a bit different. And again, the second moment of area here in the cow femur is going to be much greater than the second moment of area in the human femur. And again, the same material characterizes both, but what's enabling this bone to hold up a cow And this bone, to hold up a human being, relates to the shape of the bone, namely the second moment of area of the cow femur versus the human femur. Okay, now so far we've been talking about fairly simple shapes, bones as more or less cylindrical tubes, but you can see some interesting variations of shape amongst bones. And does this mean that the second moment of area analysis may not apply to them as much as it does in nice, well-behaved circular bones? Well, no, it doesn't mean that at all. If you look at the different kinds of shapes of bones, the long bones, of course, as we illustrated before, are more or less like hollow tubes. If you cut them across in cross-section, they will look something like this, with bony matrix out here that is bearing most of the load, and then an empty space in between, which is where you have marrow and things like that. Now, the second moment of area can be calculated fairly easily for something with a circular cross-section, but this doesn't mean that other kinds of shapes can't have second moments of area as well. So, for example, if you take a long, thin rod, rectangular rod, and if we look at it in 3 dimensions, it's going to look something like this, as opposed to our bone, which is going to look something like this, then this material right here will be fairly flexible in this direction, but in this direction, the vertical direction, it's going to be very, very stiff. All right? And so you can calculate different moments of area, second moments of area, depending upon which way the load is going. You can calculate a second moment of area for deformation, bending deformation in this direction, and it's going to be quite a bit different from the second moment of area for bending in this direction. Specifically, the second moment of area in this vertical direction is going to be much larger than the second moment of area in this direction over here. Now, when you look at the cross-section of a bone, and let's look at this one right here, our femur, it's going to be more or less circular in cross-section. There's going to be some interesting places like these ridges where muscles attach and those sorts of things, but this is going to be mostly circular in cross-section. The reason for this is that the femur has to experience loads from a variety of different directions. And so, for example, if we look at the way the femur sits in our own body, this is the left femur here, then when the body, when the person is walking forward, the main direction of movement and the main direction of bending is going to be in this plane right here. But if you're coming along and you're running and you suddenly change direction, you're going to be experiencing a stress in the bone that's going to be going this way. The point is that the stresses and strains that are experienced by a femur can come from any direction. And the best design for a bone in that instance is to have a circular cross-section, that is something that can resist flexural deformation equally with strains coming from all sides. If we come over here to Twiggy again, we can see some interesting variations of bone shape, however. You can see clearly that the long bones of the limbs are more or less circular in cross-section. This is because these can experience deformation strains coming from any direction. But if you look at bones like these neural spines along the backbone of our dog friend here, you can see that they're not quite shaped like nice circular tubes. You have some interesting knobs and things like that, but the shapes of these things are actually quite a bit far from circular. And you can illustrate this quite nicely with a larger vertebra. This makes it a bit more prominent. This, of course, is the same kind of vertebrae that's up along the thoracic part of our dog over here. And the main thing to notice here is these spines, the neural spines and the hypophyses on either side. These attach to muscles in which the strains are mostly in this direction, or in this direction, or in this direction. Very few of the strains come from either side here. Therefore, this doesn't have to be quite so strong in this dimension as it has to be in this dimension here. Now, this doesn't mean it can't be strong. There are some interesting things like bracing around the spinal cord, the neural arch here, some bracing down here at the base of the centrum. But for the most part, the strains that are experienced by this kind of a bone here are oriented in this direction or in this direction. And if you look at the cross-section of these bones right here, let's look at the neural spine, you'll see it's much longer in this dimension than in this dimension over here. And again, this is all bone, but this has a much different mechanical behavior than does this bone right here. And the different shapes have been shaped primarily by the different kinds of forces and deformations that they typically experience in the living organism. Okay, so when you're talking about the ability of bones to help animals move around, you have to consider a number of properties. You have to consider the material properties, which are embodied in Young's modulus, and the various kinds of properties that come from that. One of the remarkable things about certain materials is that they are very similar across a wide range of different kinds of animals. The bone of a mouse, for example, has basically the same Young's modulus as does the bone of an elephant. But what comes in then to make sure that those things are adapted properly to the different functions that they're being called upon to perform are these shape-related changes, namely the length of the bone and the profile of the bone. In some instances, circular is best. In some instances, blade-like is best, and so forth and so on. Okay, so that's all for today, and we will see you another time.